Okay, so we're still talking about entanglement and composite systems. So it's a kind of, or I should say composite systems and there's sometimes it's called like the density matrix, but it's the state operator. It's another way of representing a quantum mechanical state. So composite systems is how you take two different Hilbert spaces and add them together to talk about systems comprised of two or more separate subsystems, like two particles instead of one particle. And state operators are a way of describing a quantum mechanical system where you can include uncertainty in which ket you're in. So that's the idea, and I haven't really connected these two things, but I will today. And there was a question about mixed and pure states. So this row has two possibilities, right? Either P of alpha, which is a probability, is equal to 0 for all alpha, not equal to some alpha 0, and then there's a particular alpha for which the probability is 1. So in that case, the row is just this comprised of, it just looks like this. It's a projection onto a single ket. That's a pure state. That's called a pure state. And there's, a direct correspondence between a pure state and a ket. So that's case one. The other case, which is a mixed state, is when you have some uncertainty in which ket you're in. So then, this is greater than 0 for, some alphas, for, some set of alphas. And then rho is going to be a sum, right, over the different probabilities of being in different kets. So, and that's a mixed state. That's all it is. That's the difference. If you want, that you can always, if you want, rho is an operator, which we can diagonalize. So this is just another way of saying the same thing. And then, so then if you diagonalize it, of course, it'll have zeros everywhere except on the diagonal. And a pure state would be one in which there's just a single one and the rest are all zeros. And a mixed state would be a mixture of you'd have multiple you'd have probabilities of being in different kets, which would be the eigenvectors of the rho operator. So you could have 50-50 probability and then zeros, and that would be a mixed state, or some other mixture of kets. And so that's what it is. Okay, so the rho operator describes uncertainty in which ket you're in. And if you have no uncertainty in which ket you're in, then you're in a pure state. And for composite systems, it's important to distinguish entangled and non-entangled states. So there we had two cases for all, psi inside these. So this tensor product is itself a Hilbert space. And in that case, there were two cases. One is if psi could be written as a tensor product of two individual kets, each one of these, part of its own Hilbert space. that's called a non-entangled state, or I don't product state, non-entangled. And if you can't, then it's entangled. And that's all it means. Those are the classifications. So pure, mixed, non-entangled, entangled. But I haven't connected, I haven't built this bridge yet between these two things. So that's what we'll do today. But any questions about that, just as a review? Okay, and I guess the third thing we talked about was the example, and the example was 2 spin 1/2. And we saw that Hilbert space is a 4-dimensional one. It's, spanned by these basis vectors. And we saw that any, and we also talked about, so this was for the composite case. And the example we did for the state operator, we did a single spin 1/2, and we looked at the associated state matrix for a single spin 1/2. And we saw that the form of that is 1/2 identity plus b dot sigma, where this is a 3D vector in real space. And we saw that the state of a single spin 1/2 lives inside a unit sphere, like that, inside a sphere. And if the B vector sits on the surface of this sphere, then giving away the quiz answers, but that's good. These are the important things. Then we have a pure state, and otherwise, if it's living somewhere inside the unit sphere, then it's a mixed state. And why is that? In a mixed state means there's a mixture of different kets that it can be in. We're not sure which ket it's in. And we saw that it's not a unique decomposition, that if you have, draw a bigger one, I guess, if bigger sphere. If you have a sphere, a unit sphere, and you have one of these B vectors just describing the state of the spin 1/2, and it's not reaching the surface, then you can draw a chord that's perpendicular to the B vector. And there's a whole circle of these chords on the surface of the sphere that you could take, sort of like that. There's a whole circle of them. And you could describe the B as a mixture between 2 different kets, one of which is this n1 direction, another one is this n2 direction. And you can pick any n1 and 2 that are on opposite ends of this blue circle. And those would be different mixtures that correspond to the same row matrix, because they have the same B vector. Because geometrically, you can write the B vector as a sum of 2 unit vectors that you just parameterize like this. So if the B lives inside the unit sphere, then we can always decompose it into a sum of 2 unit vectors, which would be a sum of 2 pure states, right? So you can write any of these row matrices for mixed states as any mixture that corresponds to 2 states that live around this blue circle. So it's not unique. So when I say that you have a mixed state, the decomposition, which particular kets it corresponds to, it's not a unique thing. And that's just the way it is. But the description in terms of the state operator, that's unique. There will be a fixed B, and that's as much as you know about it. In particular, sort of the worst case scenario in terms of uncertainty is when B is 0. And when it's 0, you're in a completely unpolarized situation. And your row matrix is just the identity, proportional to the identity. And then you don't know anything about the direction of the spin. Oh, there's a question.
Yes, in this case, when you're looking at decomposing it into two, basically on the circle on that sphere.
Yeah.
Does it have to be just 2, or could it be 3 different vectors on that circle? In other words, can we have a mixture of multiple beyond 2?
It's a good question. Yeah, I think so. Yeah. Yeah.
I think two vectors is enough, and hat and 1 hat and 2 hat is enough. The third one, for example, is redundant. Then we probably are looking for the minimum case of the decompositions.
Well, no, yeah. The point of this demonstration is just that to connect. So in the end, rho is just it's a 2x2 matrix. And we also know that rho is supposed to, in the mixed case, is supposed to be a sum over the probabilities of, you know, some kets. And the question is this kind of decomposition unique? Is there like a single way to write down for, I give you a 2x2 matrix, is there just one way to write this? And the answer is no, there's multiple ways. So that's all it's saying. I don't know how many ways or whatnot. Here I'm just demonstrating that here are, you know, multiple ways that you can do using this geometric construction. I'm sure there's probably ways to do more. But the point is just not a unique decomposition. All right, let's see what else. Oh, and we saw that the nice thing about writing it this way is that if you take the expectation value of the spin operator, which would be, you know, the trace of rho times the vector of spin components, that gives us h bar over 2 b. So really nice. So b, you know, even though it represents this quantum mechanical state, it really is kind of the closest you can get to the classical analog of the spin direction itself, right? It's like behaves just as the classical spin would. It points along the direction of the expectation value of the spin vector, so it behaves like a classical spin. So that we'll see more of that later. Okay, any more questions about that? Sort of what we did last time before I connect these two things? All right, so let's connect them then. Let's connect. Why are these introduced in the same chapter or section or whatever? It's because, again, the idea is oftentimes you have access to some system which either lives in some environment that is itself a system, or maybe you have access to a system and for whatever reason, the system, say your qubit or something, is constructed in such a way that it forms a composite state with some other qubit, which someone else has that you don't have access to. And so you want to know what is knowable, what is the information you have just about system one. So this is kind of your info. And you want to be able to construct you want to be able to measure things and calculate expectation values and things like that, just using stuff that you have access to in system one. So you want to basically be able to compute expectation values of measurements that only work on your system. So in the composite system language, you would want to construct expectation values of just some operator A that acts just on your system. And then everything else, you don't do anything to the other system because you don't have access to it. Either, it's part of the environment, which you can't control, or someone else has it. This is like the famous Alice and Bob examples of quantum information theory. So that's the idea. So this thing, you would want it to, so you would want a notion of a state operator that just works with your information. So there'd be a state operator that corresponds to just the subsystem one. And so when you calculate expectation values of operators inside your blue bubble here, you would want this state operator to behave just like a regular state operator would, where you multiply your, you multiply it by the measurement you want to take the trace, and that'll give you the expectation value. So what would that look like in the composite, for the composite system? What would that be? Well, it would be the expectation value of a, tensor product with the identity. So we can start thinking about what that is in terms of now the full density matrix. It would be the sum over, you have 4 different indices, right? There's 2 indices for the S matrix and 2 indices for this matrix. So it'd be N12, M12, 4 indices. And you'd have the tensor product with indices N1, M2, that's for the A part. And then you'd have M1, M2 for the second subsystem. Then all of this would be multiplied by rho. It would look like this. Or rather, sorry, it's NM for this A matrix, N2, M2 for this I2 matrix. And this would be the matrix multiplication and trace. So you're tracing, so you sum over these N1, N2s, and then the matrix multiplication is the sum of over the M1, M2. So again, this is just, this is the trace, right, of rho multiplied by this tensor product. Okay, but we know that subsystem 2, the indices for subsystem 2, N2, M2, that's the identity. So this whole thing is equal to sum over N1 and N2, M1 and M2. Oh, sorry. M1, 2. And we have the A, which acts on subsystem 1, and that has indices N1, M1. And then the delta part just gives us a Kronecker delta, like that. And then you have rho M1, M2, N1, N2. And so that's equal to sum over N1, M2. You have A, N1, M1, and then I could separate out the sum over N2. So let's see, yeah, here we have a delta function, N2 is equal to M2, right? So I guess, all right, so we can drop one of the, yeah, so this is sum over N1, M1. This is sum over N2, and we're saying M2 is equal to N2, so we get rho M1 sticks around, M2 is now M2, right? And this is N1, N2. Okay, so what is it? Well, you see it's now has the form, I can now call this whole thing, this whole object, I could call this rho 1, M1, N1, right? Because we're summing over the N2s. So those go away, and we're left with M1, N1 as the indices of this matrix that we get. And I can call this whole thing just rho 1, M1, N1. And now it has only indices for the subsystem 1. And this, of course, only has indices for subsystem 1. And you see it becomes a trace because we have a leftover sum over just the first two indices for the subsystem 1. So this whole thing must be the trace of A, rho 1. Where the trace now is just over the indices of the first subsystem. So it's doing what we want. If we identify this as rho 1, right, it kind of behaves just as we would want a rho 1 to behave like. Remember the motivation. We have our subsystem that we want to measure stuff with. So we want to describe it with a density matrix, rho 1, that only we have access to over here in this blue box. And we want to do it in such a way that, we don't have to worry about what happens with system 2 or the environment. And so to make things work out, we see that what we would want is this kind of object that lets us take expectation values of operators that only act on the first subsystem. So in that case, a reasonable choice of this rho 1 operator is this object right here, which is the total density operator for the composite system, where we sum over the indices of the second subsystem. See, it's a trace, it's the same index. So in the end, what we found is that to get such an object here in blue, we use this idea from composite systems to see that a good choice for such an object, which only acts on that subsystem 1, or it describes subsystem 1. It's the state operator for subsystem 1. Is just the trace over the second subsystem, the one you don't have access to, of the full density matrix. Or if you want it to write it in components, it's the sum over N2 of rho M1, N2, N1, N2, like that. Does that make sense? So if you have a subsystem and you want to describe its state, then what you do is you just trace out over the states for the other subsystem you don't have access to. And that's how the two are connected, really. The composite system lets you describe systems that are not isolated, that are either entangled with other systems, like in this case, 1 and 2 might be part of an entangled composite state, or maybe 2 is a big environment that you don't have access to. And so whenever you have that situation, to describe what you can do with your own little subsystem, what you do is you take the full density matrix of the composite system, which might be a pure state, and you trace out the degrees of freedom for the system you don't have access to. So if you don't know about the other subsystem, then you trace it out, and that's how you do it. Any questions about that? If I can do more, I'll do more examples of this. No, we're good. All right, so what else? It's good to keep in mind this kind of notation. Sometimes you want to trace over. So the way these operators work, right? If I have a general operator on like a tensor product space and so on, what I would do is I would have it's still a matrix, so it has 2 indices for each space. So I would say, N1, N2, N3, and so on. That's for the first index. And then I might put like a semicolon, and then I'd put an index for the other index, right? Because it's like a matrix, so it needs 2 indices, M1, M2, M3, right? And then when I say something like, let's trace over the particular subsystems, right? I take the trace sub I or something. Then what I would do is I would, what would I do? I would sum over, N sub I of, N1, and then I'd, pick out that N sub I. And over here, I would set that M equal to N, right? It's a trace, you look at the diagonal elements, and I would sum over those. Those are the partial traces. These are called partial traces. And I've demonstrated to you that if you have a subsystem that you don't know about, like this 2, then you do this partial trace of the full density matrix in order to get the state operator for just the part that you do know about, that you have access to. So that's the idea. Okay, so let's do some examples. An example would be, suppose we had a pure state for the composite system. Well, then I would be able to write it, as a sum. It's a pure state, so it's represented by some ket. I would be able to write it as some coefficients, right, of tensor products of the 2 individual Hilbert spaces. And I know that, the full row would just be like that, right? So that's a pure state for a composite system. And then you might ask, what's the density matrix for just the subsystem 1? Well, you would have to take the partial trace with respect to subsystem 2 of, this total density psi sign. And what is that? Well, it's well, you can construct this thing psi, right? You would take these kets and make them bras and multiply by the complex conjugate of theseCij's. Right, so you would get sum over I, J, you need two more indices, K, L. What would you get? You'd get C, I, J, and then C, K, L star. You would get phi I from this ket, and here you would get phi K from the bra part. And then what happens to these psi's? Well, they form just an inner product of psi L and psi J. Because you remember you showed that if you have, I forget where this was, the midterm? You showed that the trace of an operator like this, you know, I could insert a completeness relation. And so this is equal to just things reversed. So if we take psi here and we trace it over just the second subsystem, then we would get a trace of this type, right? Where this would be psi psi J and psi L, right? And so when you take the trace with respect to those psi's, the subsystem corresponding to the psi's, then you just get the inner product between the two reversed. So that's what happened here. We constructed this row and we took its trace with respect to subsystem 2. We got these coefficients. We got this guy, which is the ket from this guy. We got the bra, which is the bra from, you know, this part of it, the row. And then the psi's, they dot into each other like this because of this property of the trace. Is that okay? Does that make sense? Maybe.
I think it does.
Okay, so we can continue on, right? If these are orthonormal, you know, like if we're using an orthonormal basis, which we would be when expanding. Remember, this expansion, we pick the basis such that it's just a combination of the basis of the two individual subsystems, and they're both orthonormal. So these guys are orthonormal. So this just becomes a sum over ijk, because now L is equal to J. And it becomes Cij, C star, K, and now again, L is equal to J, so this becomes J. And it's phi I, phi K. And you see what happened. Similar kind of thing happened where this just depends on I and K, and then these C's, you're summing over the J. So I can just call this a sum over I and K, and then just some other coefficient, which only has indices corresponding to the first subsystem. And it'll be, you know, phi I, phi K. So you see what happened here. If you start with a pure state, when you trace over one of the subsystems, you're in general left with some kind of mixed state. Or see this in general won't be a pure state. It'll be some mixture. And we can see that explicitly if we pick theseCij's to be diagonal. If we just say that they're equal to Ci delta Ij, right? If we make them, choose them to be diagonal, we can just make a nice basis where, you know, the I and j, the off diagonal pieces are 0, and we just get, you know, it's sort of like having a, it'd be like up plus down for the spin 1/2. But if you have such a thing, just diagonal coefficients like this, then I can show you explicitly that it's a mixed state. Because then this row 1, right? What would it be? Well, it would be sum over ijk. Now going back to the step, it'd be Ci, right? And then so if this is diagonal, Cij is just Ci and I has to be equal to j, then this j has to be equal to I, right? So this becomes Ci star from this guy, because both of these are diagonal, and then this becomes phi I. And you see that is nothing but, you know, sum over, I guess I got rid of the j, there's no j and k, because both j and k have to be equal to I. See, if you go back here, it's diagonal, it means I is equal to j. So that kills the sum over j. And so this is I, right? And so then k has to be equal to I also, and that kills the sum over k. So both of these are just Ci's. And then, so you just get this. And that's just some numbers, probabilities, right? Squared of being in ket phi I. So you see it's a mixture. So that really should make it quite obvious the connection between composite systems and mixtures. The idea is if you have a composite system, but you only have access to one piece of it, one subsystem, then even though your entire system may be in a pure state, meaning describable by a ket in the composite Hilbert space, if you want to know about just the information that you have about your subsystem, then what you have to do is you have to trace out over the other subsystems by doing these partial traces over those indices for those other subsystems. And what you find then, generally, if you start in a pure state for the whole system, when you trace out, you get a mixture for your subsystem. So the uncertainty in your inability to access the information about the other subsystem generates uncertainty in your description for your little subsystem. So it should make intuitive sense. If you don't know something, if you don't know something about a piece of your system, you're going to have some, classical uncertainty in its state. So that's how the two are connected. So let's do an even more concrete example, right? Any questions though, before I do the even more concrete example? This is still a kind of abstract example, but.
I have a question. So, about phi I and psi j, where they come from? Like, what are those?
Phi I would be a basis for, the first Hilbert space, and psi j would be a basis for the second Hilbert space. They have different indices because in principle, you might have different dimensions for the Hilbert spaces in principle. It's a tensor product. So it means, this guy corresponds to one subsystem, this is to the other one.
So there is no assumption when you're tensoring two systems, there is no assumption of having the same dimension.
No, they don't have to have the same dimension,
Okay.
no.
Okay.
That's why I don't write any limits here over these guys. The limits are whatever they have to be to get the dimensions to match.
Okay. But all of them, but the dimension is the power of 2, right? They are.
No, okay, so that's not entirely true. Where I did make the assumption is here. See, I'm saying here that the two indices were diagonal. So here I'm assuming it's the same dimension, I guess, for the Hilbert space. Yeah.
Okay.
Yeah. I don't think nowhere else do I ever, everywhere else I dot L and J together, which corresponds to that second index. So that is for Hilbert space 2. And the first index has to do with, it has the number of indices is for, Hilbert space 1. So everything is okay until I assume this. Here I'm saying that, that there's the same number in the two Hilbert spaces. So yeah, I guess that's true.
Okay, thank you.
And I mean, to tell you the truth, this is all too much generality, probably, because we only care about, when we do this kind of thing, our composite systems are always going to be like 2 spin 1/2s, 3 spin 1/2s. It's usually the same Hilbert space dotted into itself. Not always, though. When we do addition of angular momentum, you will add an orbital angular momentum and a spin angular momentum, and those, it's like spin 1/2 and then some large spin, right? Because the orbital spin could, the orbital angular momentum, the electron could be whizzing around some high orbital. So it could have very large angular momentum, and that's a much higher dimensional Hilbert space. So yeah, not always true. Sometimes you have to be careful about, these indices. But not for now. I'll do that next chapter we look at. But all right, let's do an even more concrete example. The 2 spin 1/2. Suppose our composite system is the singlet, which we looked at. It's up, down, minus, down, up. And that has this form that it's, sum over some diagonal coefficients of, phi I, psi I. It's just they're backwards with respect to each other. This one's up and then down, this one's down and then up. But that doesn't matter. These coefficients are still, it still has this form, right? There's 2 coefficients, this one and this one, plus 1 over square root of 2 and minus square root over 2. And so it has this form. So then I can tell you what the partial, say I don't have access to the second spin, right? That's, Bob has it and I'm Alice and I don't have it. So my description of this spin, right, would be the trace over Bob's spin or subsystem 2 of the full density matrix, which is, psi. And I just showed you from the general case up here, that sum over I, the magnitudes of these CI coefficients squared, phi I. So what is that? Well, the first coefficient is 1 over square root of 2 squared, and the phi I here for this coefficient is up arrow, so that would be up arrow, up arrow. The other coefficient, right, would be minus 1 over square root of 2, but it doesn't matter because the whole thing's squared. And what's the phi I for that guy? It's a down arrow. So you get a down arrow, down arrow. So that whole thing is 1/2 up arrow plus down arrow. And lo and behold, it's unpolarized, right? It's the identity. you want to write it in matrix notation, it's 1/2 1 1 0 0. So what's it mean? It means if you have, even though you have a composite system that's in a singlet state, which is entangled, if you only have access to one of the spins, then basically what you have there is a completely unpolarized spin. You don't know anything about its direction. So even though you started in a pure state here of this entangled guy, if you have only access to one of the spins, then you're in a completely mixed state, like a state of maximal uncertainty. All right. So any questions about that? It's a pretty important example.
This was the state was state singlet.
Yeah, we started with this state. It's called a spin singlet. It's a state of 2 spins.
Yeah, I had a question. Like, yes, the last time you showed that it's this state is invariant under rotation.
Yeah.
And that that rotation theta and phi, they are arbitrary angles
Yes, arbitrary angle. Yeah.
between 0 and 2 pi.
Well, yeah. I mean, theta is the axis from the z-axis, so it goes from 0 to pi, and then phi is the azimuthal one. So
Yeah. So to me, only the origin can be invariant under any arbitrary rotation.
yeah, but that's not true for the composite system. That's why it's weird, right? If you have a composite system of 2 spin 1/2s, then even though it makes no sense classically, I don't know how well you see my fingers. If you have 2 spins, generally whatever I think of doing, right, I can't construct a state that's spherically symmetric, right? No matter what I do to the 2 spin 1/2s, no matter how they point, I'm still going to get something that will rotate around in space somehow. So classically, it's completely nonsensical to have such a state, but I showed you explicitly that quantum mechanically, you can have a state of 2 spin 1/2s that is rotationally symmetric. That it looks complete. It looks exactly the same when you rotate the system around. It's just, yeah, I don't know. It's the magic of the spin singlet.
Okay.
I agree, it's sort of hard to envision classically, but that's why it's better to lean on the mathematics in quantum mechanics. I firmly believe that that our brains are just classical in nature, and but so what? That's why we have mathematics as our as our guide. So all right. Okay, those good questions. Any more about this? Okay, so something else. Again, I really want to emphasize this idea about information and how much of it there is. So we can introduce the idea of entropy, which it tells you something about how much information you could, in principle, find out about a system. Right? I like to think about it that way. And it's an operator. So it's something you can measure. So it corresponds to an operator. Or sorry, I guess the way I'll present it. So it's going to be a it's going to be a number. So it's going to be a trace. It's the trace of row, the full density matrix, log base 2, so that it's in bits, row. So these are, of course, this is an operator and we're taking its trace. And for our example of a single spin 1/2 particle, for instance, this number ranges between 0 and 1. So the state, the amount of information, and so what do we have here? So suppose for our spin 1/2, your row is just the unpolarized state, like this, right? Then what would you get? Well, you would get S is, let's see, minus the trace of 1/2. So this is the identity log of log base 2 of 1/2, 1/2, right? And so this is trace of, and this is diagonal, so it's 1/2, and I can take the log in here. This is minus trace, and the log of log base 2 of 1/2, it's -1, right? So then this minus sign cancels here, so it's the trace of 1/2, 1, 1, 0, 0. So that's 1/2 plus 1/2 equals 1. What it means is an unpolarized state, right, has an entropy of 1 bit. It means that you can in principle get a bit of information about, there's like a bit of uncertainty. There's exactly 1 bit of uncertainty in the direction of your spin, right? And that makes sense. If it's unpolarized, you don't know which direction it's pointing, but that's still just 1 bit of information, because we know that the spin is either going to point, up or down along some direction. So that's the most amount of uncertainty you can have, is when the spin is completely unpolarized. But if you have a pure state, right, then or let's do it even more. Let's do an even a better example, right? We could have rho is equal to some general decomposition, right, of probabilities of being in some states. Then this S, I could calculate it, right? Minus sum over n. I'm taking the trace, so just the diagonal elements like that. And then what? Then I would put in completeness relations, right? Oh, so by the way, if rho is this, then of course log of rho as an operator, since it's diagonal already, then it would be just sum over n log of these pn's, right? Of n, like that. So then I can start expanding everything out, right? Put in some completeness relations, replace rho with, the sum over these probabilities, and you would get n. This would become p l here. Here's an L. This would be a log of the p n. Here we have m n. So I put in some completeness relations with L and M, and since I'm picking out this log rho acts on this n, so it's going to pick out just the log of the p sub n piece. That's this guy. And over here, I put in a completeness in here, so it picks out the P sub L piece. So now we can start multiplying everything out, extracting out these P of L's, right, and getting delta functions everywhere. So you get minus sum over N M L of, let's see, PL. We've got log of Pn, those are numbers that just come out. Then you have a delta function with N and L, a delta function with L and M, and a delta function with M and N. So a lot of the sums cancel out. You get minus sum over N M. So let's do one of them. Let's do the sum over L. L has to be equal to N and M. So that's good because M and N are equal. So if you do a sum over L, L has to be equal to N. You get that. And then we're just left over with this delta function. So you see it just becomes a sum over N Pn log Pn. So we already showed that when these are both a half, then you just get one. But also if P up, for instance, is 0 and P down is 1 or something like that, if you're in a pure state, then S is equal to 0, right? Because the log of 1 is 0, and then the other term is 0. So you just get 0 if you're in a pure state. So you see this S kind of spans the range from 0 to 1, right? And it's 0 for a pure state and 1 for a completely mixed state where you don't, where you have maximal uncertainty. And that's what I like to emphasize, is that whenever I tell you that a system is, some ket like this, we know that there's still uncertainty in things like the values of measurements and things like that. But in a very strict sense, if your system is, represented by a vector in a Hilbert space, that's the most amount of information that you can possibly have about the system. There's nothing else you can find out. Nature doesn't allow you any more information. And that's kind of, you can prove that strictly by looking at this S quantity, which is the entropy. It's, there's no more uncertainty. The entropy is 0 for a pure state. And for a mixed state, it's for this maximally mixed state, it's 1. And otherwise, you might have some partial uncertainty. So it might be somewhere between 0 and 1. And this is a nice kind of quantity that quantifies it. Usually we don't talk about entropy in bits. Usually the log is base E, the natural log. You could say that it's the information in nats. But I like bits because for things like qubits and quantum information, that makes a lot more sense. A single qubit is, in a strict sense, a qubit is just like a bit. It's a 0 or a 1. So that's why, and you can sort of see that, even though it's described by this complex state operator thing, which seems to have many degrees of freedom, you still calculate the sort of informational content, right, in your qubit by calculating, say, the entropy. It's always, between 0 and 1. So we'll talk about quantum computing, I guess, next time. I'll emphasize that again, that you don't gain any extra information by doing quantum mechanics. Just because your bits become quantum mechanical doesn't mean you all of a sudden get more information out of them. It's not how it works. And we'll see that explicitly when we talk about quantum computing. Because when you measure something, right? You still either get one, two different possibilities. Remember, the dimension of the Hilbert space tells you the number of possible measurement outcomes you get. And for a qubit, it's always two. So it's always a 0 or a 1. And so that's the amount of information you have. And it's confusing because, people like to, or, we talked about this block sphere business, which I guess I erased now. Well, we talked about the block sphere, and it seems like a quantum mechanical bit should have somehow more information because its state is describable, but by this complicated block sphere thing. But you don't measure the quantum mechanical state. That's not a measurable thing. In the end, you have to do some kind of readout where you do a measurement, you do an expectation of some operator, and that has the same amount of information that a classical bit would have. But I'll say more about that later. I just want to at least introduce you to the concept and at least get you to think about this connection between composite systems and uncertainty in the state of your system, your subsystem. So, and it'll all come together, I hope. But yeah, any questions about that?
Would you please remind me of the definition of the log of an operator?
Yeah, that's a tricky one, but well, I'll explain it this way. If you have an operator A, then you can diagonalize it. And then I can write A as some eigenvalues and some eigenvectors like that. And then I would define the log of A as follows. Oops. So I would do it that way. It's harder to assign. You also can define it as a power series, but you don't want to expand the log around 0. So I guess.
Yeah, that's what I thought, and it was like.
You could do like this if you want. Like you could do. You could probably do something like. Do something funny like this and expand this part around 0. And you'd have a sum over n. However, I forget how the power series for this works. I'm sorry, but you could do that. That wouldn't be too bad. But I mean, it's basically just this. You take your A, you diagonalize it, and then in that basis, of course, the log of A is just the log of the diagonal elements. It's probably the easiest way to think about the log of it. That's what we did here. All right, more questions? I want to mention something, the last bit, I want to talk about time dependence. And that's easy to get because notice I can take the time derivative of any one of these projection guys, real easy. I know how to do this. It's chain rule. I know what the Schrodinger equation is, right? That this guy will pick up an h when the time derivative hits it, but when it hits this guy, it'll pick up a minus h, right? Because when we take the Hermitian conjugate of both sides of the Schrodinger equation, this I becomes a minus I. So the other bit is, phi h but that's real easy. So that's just, you know, the commutator of H and phi phi. Well, now I can just take the probabilities P alphas here and sum, you know, both sides like that. So I immediately conclude that, you know, the equation of motion for your rho operator is just as follows, right? It's just, this is the Schrodinger equation. This is the equivalent of the Schrodinger equation, but for your density matrix. And you can also write down the unitary evolution of this guy. You know, each one of these will evolve, just as, you know, we talked about with unitary time evolution. So on one side, it will evolve with a U. On the other side, it will evolve with a U dagger. So this is the way the density matrix or the state operator must evolve in time, right? It's just the sum over these bras and kets, then each bra and ket will evolve with a U dagger and a U. So, you know, this is how the whole thing evolves. Real easy. And you can, I'm out of time, but you can look at the notes. All right, this is a very simple example, but you can show that if rho, if you do this example of spin 1/2, right, and we know that rho is given by this guy. So this is a constant, this is a constant. So B is the only thing that can sort of depend on time, right? You can show that the equation of motion for B is exactly the same as the classical equation of motion for, you know, the spin. So this would be if H is a magnetic field, the energy of a spin in a magnetic field, you know, pointing along the z-axis, say. Yeah. Maybe I'll do that next time, just quickly. But what we'll do next time is just write down all the postulates of quantum mechanics again, but with rho instead of the kets, just for completeness, to sort of complete the picture. But yeah, so hopefully you've seen today that it's better to think about rho as a description of your state because it allows you to consider things like subsystems and uncertainty in the state of your system due to your inability to access information about, you know, other pieces of the system, like an environment or an entangled piece of the system somewhere else. And that'll be relevant when we talk about computing, decoherence and things like that, and, you know, sort of continue building the full picture. So this is a kind of extension of what we've been talking about in terms of Hilbert spaces. Now we see that instead of talking about vectors, it's better to talk about these state operators, which can include uncertainties in which ket you're in. It's a much better description, and allows us to talk about, you know, subsystems